Hello everyone, welcome to VYAS Edification. In this session we are going to discuss NCERT and exercise solutions of chapter number 10 mechanical properties of fluids. Clear? So in this session you will find detailed solution of each and every question, as well as you will find the theory behind that question also. It means overall you will understand the whole concept of this chapter through the questions. Clear? So now we are going to discuss each and every question. So concentrate on a screen. Let's start. Now dear student, we are going to discuss question number 10.1, and in this question we have three parts of this question, part number A, B and C, and in this question it is given to you explain why. Number 1, the blood pressure in human is greater at the feet than at the brain. Clear? So my dear student, this is actually logical question. Now actually we know the blood pressure, or if we talk about gauge pressure is actually given by so if we talk about gauge pressure is given by P equal to rho GH. Clear to everyone? Now we can say as the height of a column, as the height of a liquid column increases, we can say pressure increases. Clear to everyone? So now we can say the blood pressure in human is greater at the feet. Why? Because we know if we talk about the column of a blood from the feet, we can say the height of a blood column that is more compared to height of a blood column at brain. Clear? So now we can say because value of H is more in at the feet. Value of H is more at feet, so we can say pressure is more at feet compared to brain. Clear to everyone? So in short I can say because height of a blood column is more at the feet compared to brain, that's why we can say pressure in human is greater at feet compared to brain. Clear to everyone? Now we are going to discuss part number B. Clear? So in part number B it is given to you atmospheric pressure at a height of about 6 km decreases to nearly half of its value than sea level, though the height of atmosphere is more than 100 km. Now listen carefully. Actually we know as we move away from a surface of a earth, or we can say as we move from the surface of a earth to a certain height, definitely density of a air decreases. Clear? But actually the density decreases not in a uniform form. Generally it is seen that density is varies like the e to the power minus times ky. Clear? So we can say if we draw here a graph between y and density, then we can say it should be like this. Clear? Or we can say this is exponential decreasing curve. Clear? We can say this is exponential decreasing curve. It means we can say initially density of this air decreases more compared to after some time. Clear? So we can say if we are talking about initial increase in length, if we are talking about the height of 6 km, so height of 6 km from the surface of earth, the density decreases up to half. Clear? But because we know height of an atmospheric column we are taking approximately equal to 100 km, so rest half of a density decreases from 6 km to 100 km. Clear? So answer is very simple here, because the variation of a density in our atmosphere is not uniform. As we move away from a surface of a earth, the density decreases, we know very well, but initially density decreases, the decrement of a density is more in initial height compared to later one. Clear? So now we can say that from 0 to 6 km density decreases to half, and the rest half of the density it is decreases after 6 km to 100 km. Clear? So this is all about part number B. Clear everyone? Yes. Now we can say if I am talking about part number C, hydrostatic pressure is a scalar quantity even though pressure is a force divided by per unit area. Now listen carefully. Actually we know, let's suppose if I draw here one diagram, let's suppose this is a container, and in this container let's suppose we have a liquid up to this level. Clear? Let's suppose I have liquid up to this level. Clear to you? Now let's suppose if I am saying here we have a ball, let's suppose this is a cricket ball. Clear? Now we can say because this is inside this liquid, so definitely we can say according to Pascal law, forces that is exerted perpendicular to this surface like this. Clear? And now we know this force is exerted per unit area, that is known as pressure. Clear? So now we know that pressure is equal to force per unit area. Clear? Now if I am talking about this small areas, clear, and you know force is a vector quantity, it means the pressure should be a vector quantity, but it's not. Why? Because we know in a pressure we have a magnitude. Definitely let's suppose we are getting value 2 Newton per meter square, then we can say definitely it has some magnitude. Yes. If we are talking about unit, definitely it also have some unit. Yes. But what about direction? Clear? So now we can say if we are talking about hydrostatic pressure does not have any specified direction. Clear? Actually we can say the direction of a force is actually from all the sides on this ball. Clear? It means we can say we do not have any specified direction. That's why we can say although pressure is having direction, but the direction is not a certain or unified or a particular direction. Clear? So we can say we cannot put this pressure, hydrostatic pressure, in a vector quantity. So we are putting this physical quantity in scalar quantity. Clear to everyone? So this is all about this question. Clear? Now student, we are going to discuss question number 10.2, and in this question we have to give answer of some questions. So actually in this question we have total 5 part A, B, C, D, E, and now we are going to discuss each and every part one by one. So if I am talking about part number A, so in part number A it is given to you, we have to explain why. Clear? Number 1, the angle of contact of mercury with glass is obtuse while that of water with glass is acute. Clear? So now dear student, definitely you have listened about two terms, cohesive force and adhesive force. Clear? So cohesive force is what? We can say force that is acting between same type of molecule, we can say that is cohesive force, and adhesive force means we can say that force this is acting between two different types of molecule. Clear? So if I am talking about part number A, so I can say let's suppose I am taking here let's suppose this is a capillary tube. For example, I am taking this is capillary tube. Clear? And if I am talking about mercury with glass, so let's suppose I fill here mercury, so definitely we will find here the shape of this mercury meniscus, it should be like this. Clear? But if I am talking about we can say if I am talking about water on a glass, so this surface should be like this, this meniscus will be like this. Clear to you? So now why this is happening, this is very very important. Now we can say actually between this is mercury and this is for water. So if we are talking about mercury and glass, definitely we can say here whatever forces that is acting, I can say they are the adhesive force. Clear? And we can say between mercury molecules we have here cohesive force. Clear? So in mercury and glass combination we can say cohesive force is more compared to adhesive force. Cohesive force is more compared to adhesive force. Clear? So we can say when cohesive force is more, definitely all molecules of a mercury it wants to come at the middle, because we can say force between mercury molecules is more compared to force between mercury and glass. Clear? That's why we can say here we will find angle of contact that is obtuse. Clear? Or you can also say how can we decide here angle of contact. So now we can say like this, let's suppose how can we decide. Actually first of all at the point of contact we draw here a tangent. Clear? So at the point of contact we draw here a tangent like this, number 1. Clear? And we also draw a tangent that is tangential to this glass surface like this. Clear? Or we can say like this. Now we can say the angle between this one, it actually decides angle between this is a obtuse angle or acute angle. So we can say definitely you can say this theta is greater than 90 degree. So we can say this is obtuse angle. Clear to everyone? Yes. But if I am talking about water, Clear? So in a water case, now we can see, you can see actually here we also have cohesive force and adhesive force. So in a water and the glass contact, we can say adhesive force is more compared to cohesive force. That's why this water always wants to spread on a glass. Clear? So in this situation we will find adhesive force greater than cohesive force. Adhesive force is greater than cohesive force. Clear? So now we can see how can we draw here angle of contact. So first I am drawing here a tangent. So this is a tangent. Clear? And I am also drawing here one tangent, that is along this glass. So I can say this angle is known as angle of contact. Clear? This angle is known as angle of contact, and definitely we can say here we are getting theta. This value we have less than 90 degree. Clear? This theta we are getting less than 90 degree, and here we are getting theta. This one is greater than 90 degree. Clear to everyone? So now we can say here in this situation we find acute angle, here we will find obtuse angle. Clear to everyone? So conclusion of this question is here, when cohesive force is more compared to adhesive force, at the time you will find this type of meniscus, as well as we can say here you will find angle of contact obtuse. Clear? But if I am talking about when adhesive force is more than cohesive force, in this case we find acute angle, as well as you can say here adhesive force is more compared to cohesive force. Clear to everyone? So this is all about part number A of this question. Clear? Yes. Now we are going to discuss part number B, and in this question it is given to you water on a clean glass surface. Water on a clean glass surface tends to spread out, while mercury on same surface tends to form drops. Definitely again we are having same answer, because between water and glass we can say cohesive force is that is adhesive force is acting. So definitely in water and glass adhesive force is more compared to cohesive force. Clear? That's why we can say definitely water will spread out on the glass slab. But what will happen with mercury? So if we are talking about mercury, so on the mercury molecule, because adhesive force is less compared to cohesive force, so definitely mercury molecules always wants to form a droplet. So this is the answer of part number B. Clear to everyone? Done. Now if we are talking about part number C, so in part number C it is given to you surface tension of a liquid is independent of area of a surface. So first of all let us try to understand how for what vector or how can we define value of surface tension. Clear? So let's suppose I am taking here a top view of any container. Clear? So let's suppose I am drawing like this. This is the top view of a container. Clear? And let's suppose we can see here we have a liquid also. Clear? This one. This is the top view of a container. Let's suppose we have a cylindrical container and I am observing from top. Clear? So this is a top view. Let's suppose I am drawing here an imaginary line. Clear? So this imaginary line I am drawing like this. Clear? Now we can say how can we define here surface tension. So definitely on this line a force that is acting perpendicular. On this line we can say a force, this is acting perpendicular to this line like this. Clear? So if I am saying this value we have length L. Clear? And a force F is acting like this. So surface tension is defined as S equal to F by L. Clear? So force acting per unit length of this imaginary line, this is known as surface tension. So from here you can say surface tension depends on a nature of a liquid. It also depends on a temperature. Clear? But it is independent of a area. Clear? So now we have to find like this, surface tension of a liquid is independent of area, definitely, and you can prove like this. Clear? Because here we are not getting any term related to area. Clear? So this is all about part number C. Now if I am talking about part number D. So in part number D it is given water with detergent dissolved in it should have small angle of contact. Clear? So actually we know, if you know formula of capillary rise, listen carefully. If you know formula of capillary rise, this is given by 2 rho cos theta divided by we can say this is given by, just a minute, if I am talking about capillary rise, this is given by 2, clear, and we can say this is rho g r, and we can say this is 2s cos of theta, clear. Here you can say this S is what? S is a surface tension, theta is the angle of contact, and we can say rho is the density, g is acceleration due to gravity, and r is what? Clear? R is, we can say this is the radius of capillary tube, clear. So now we can say if we are talking about small angle of contact, it means we are saying that this cos theta value is less. It means we are talking about 0 degree, 10 degree, 15 degree, 30 degree, clear. When theta value is small, at that time definitely we can say this cos theta value will be more. Yes or no? Because we know cos 0 equal to what? 1, and cos 30, this is equal to root 3 by 2. So definitely we can say as theta decreases, the value of cos theta increases. Value of cos theta increases, it means we can say value of H increases, clear. So now we can say what is the purpose of detergent? Purpose of detergent is what? To decrease surface tension, as well as we can say so that it may move to a certain height. So height increases, or we can say height of a liquid column increases. So what will happen? Actually this will remove that from that particular hole, clear. So now we can say it is very clear to us, if theta is less, cos theta is more, and we can say height of a liquid column or the detergent, it will be more, and definitely we can say it can remove dirt more effectively, clear. So this is all about part number D, clear. Now if I am talking about part number E, clear. So in part number E, it is given to you a drop of liquid under no external force is always spherical in shape, clear. So actually we know if we are talking about a drop, a liquid drop, clear, and we are assuming there is no any external forces acting. So definitely we can say the shape of that spherical drop, the shape of any drop, it is due to surface tension only, clear. And what is the property of a surface tension? Property of surface tension we have that it always tends to minimize its surface area, clear. So for a given volume, if no external force is acting, at the time the sphere, we can say sphere is having minimum surface area, clear. Again I am saying what is important point here. For a given volume, sphere, it is having minimum surface area, clear. That's why we can say that a drop of liquid under no external force we always find in a spherical in shape, clear. So this is all about this question. Now student, we are going to discuss question number 10.3, and in this question, this is a question related to fill in the blanks part, and in this question it is given to you number A, surface tension of liquid generally, fill in the blanks, with temperature. So let us try to understand. This is the general logic. If we increase temperature, definitely surface tension decreases, clear. So direct answer we have for this question, surface tension of liquid generally, I can say decreases with temperature, clear. So as the temperature increases, I can say surface tension of liquid decreases. Why? Because as the temperature is increasing, we can see the bonding, or we can say the cohesive force between the molecules is getting weaker and weaker, clear. That's why we can see here that surface tension is decreasing, clear to you? Yes. Now if I am talking about part number B, in part number B it is given viscosity of gases increases with temperature. Why? Viscosity of gases increases with temperature, whereas viscosity of liquid decreases with temperature. Why this is happening? Because we know if we are talking about gas molecules, so gas molecules are having random motion, and as we increases temperature, definitely the randomness of gas molecules increases, clear. So more is the temperature, more is the randomness of a gas molecule we will found, and as well as we can say viscosity increases, clear. But what in a liquid? As you increase temperature, the bonding between two liquid molecules, it decreases, it getting weaker, and we can say at the time viscosity of liquid decreases, clear to everyone? Clear. So this is all about part number B. Now if I am talking about part number C, in part number C it is given for solids with elastic modulus of rigidity, shearing force is proportional to shear strain, clear. Why? Because let's suppose if I am saying to you stress is equal to modulus of rigidity, let's suppose K, modulus of elasticity K times of strain. Clear? So if I am talking about shear stress I can say F shear divided by area. This is equal to, here we will find modulus of rigidity. Clear? Or you can say shear modulus, and I can say multiplied with strain. Clear? So if I am talking about shear, if I am talking about shear force for a solids. Clear? So for a solid, shear force is directly proportional to shear strain. Clear? So here we are getting answer. This is shear strain. But what will happen in liquids? Clear? So actually, definitely, let's suppose if I am talking about these two layers. Clear? And let's suppose here liquid layer is in contact, and let's suppose this is ground. Clear? And let's suppose it is at a certain distance d, and here we are having velocity of a liquid, that is v. Clear? And here we have velocity v equal to 0. Clear? So in fluids actually we define velocity gradient. What we define? Velocity gradient, and we can say this is defined as delta v by delta, we can say this is defined as delta v by delta t. Clear? So now we can say important part we have, how can we define rate of how can we define shear force related to fluids. So definitely we can say it is defined like this. I am just writing here. It is defined like this. Just a minute. Yes, I can write like this here. F by A, this should be equal to neta delta V by delta T. Clear? So now we can say here this force is defined as rate of shear strain. Clear to everyone? This force is defined as rate of shear strain. So here we are getting our answer. This is the rate of shear strain. Rate of shear strain. Clear to everyone? Yes. Now if I am talking about part number D, so in part number D it is given to you. In part number D it is given, just a minute. Yes. Now if I am talking about part number D, for a fluid in a steady flow, the increase in flow speed at a contraction follows. Now listen carefully. Let's suppose if I am talking about this type of cross section area. Clear? And let's suppose I am saying here, first I am taking this section 1 and 1 dash. Clear? Let's suppose this is 2 and 2 dash. Clear? So definitely we can say here, let's suppose the liquid is flowing from this side and it is going outside from this side. Clear? So definitely we can say, if we are talking about steady flow, clear, and we are assuming there is no loss due to this pipe walls, at the time we can say conservation of mass we can follow. Clear? And according to conservation of mass we can say A1 V1, this should be equal to A2 V2, or you can say you can apply here equation of continuity. Clear? So equation of continuity follows conservation of mass. Clear? So definitely we can say in this question we have answer conservation of mass. Clear? Now if I am talking about part number E, so definitely this is just a theoretical question we can say. For a model of a plane, let's suppose if we are simulating a model or simulating a model for an aeroplane, okay, fine, in a wind tunnel, fine, turbulence occur at a speed, turbulence for a actual plane. So correct answer we have, that is greater. Clear? So actually let's suppose we have a wind tunnel, and in wind tunnel we are actually simulating same situation as for an aeroplane that we will find at a certain height. Clear? So definitely here we can simulate, but here turbulence will occur at a greater speed compared to turbulence that occurred at the actual position. Why this is? Because here we can say if our model sustain for a greater turbulence, definitely it can sustain for a certain height also. Clear? That's why we can say turbulence occur at a greater speed compared to actual situation of a plane. Clear? So this is all about this question. Now student, we are going to discuss question number 10.4, and in this question it is given to you, explain why. Number 1, to keep a piece of paper horizontally you should blow over it, not under it. Now let us try to understand this situation by this paper. Clear? So let's suppose I am having this paper, and let's suppose I want to keep this paper horizontal. Then what I have to do? I have to blow air that is above paper or below paper. Now first let us try to understand all the forces or the pressure that is acting on this paper. Clear? So in this paper we can say definitely you can say an atmospheric pressure is acting in a perpendicular downward direction like this, clear? And below we also have same atmosphere, so we can say atmospheric pressure is acting like this, clear? Now let's suppose if I am blowing air on the top, or we can say over this paper, then what will happen? It means what I am doing, listen carefully, what actually I am doing, I can say, let's suppose this is indicating a paper. If I am blowing air from on the over of this paper, it means I am increasing velocity on a top, and definitely at the same time I can say this velocity becomes less compared to the over part, clear? Now when velocity is increasing, so at that time you know very well, if we write here P plus half of rho v square plus rho g h, this value we have constant, clear? So definitely if we are talking about datum, so datum is almost same, so we can say this will not contribute in any factor, clear? So definitely if we are increasing velocity, definitely we can say on over part we can say pressure decreases, clear? At the same time you can say pressure is increasing at the bottom, so what will happen? Definitely we can say pressure exerted from a bottom, it will be more compared to pressure exerted at the top, and definitely at that time I can hold this paper horizontally, clear to everyone? So this is an explanation of part number A, clear? Now I can say what about part number B? In part number B it is given to you, when we try to close a water tap with our finger, fast jet of water gushes through the opening between our fingers, clear? This is a general common experience. Let's suppose a water is coming out from a tap, and let's suppose you are actually making a very small opening by using your fingers, clear? At the time what you are doing, if I am talking about continuity equation, clear, I can say A1 V1, this should be equal to A2 V2, clear? Or directly from here you can say AV, this value we have constant, clear? We can say this value we have constant. It means we can say this V is inversely proportional to area, clear? So whenever we are making a small opening by using our finger, it means we are decreasing here area. So when area decreases, it means definitely velocity increases, clear? So when we try to close a water tap with our finger, definitely the speed of a water that increases, clear? So this is all about part number B, clear to everyone? Done. Now if I am talking about part number C, the size of a needle of a syringe control flow rate better than thumb pressure exerted by a doctor. Now listen carefully. Actually if I am talking about Bernoulli principle, Bernoulli said P 1 by 2 rho v square plus rho g h, this should be equal to constant. So from here you can say pressure as well as this expression of a kinetic energy per unit volume, both this is pressure per unit volume and this is kinetic energy per unit volume, both are contributing in total energy, clear? But we can say if we are talking about needle, so for a needle definitely we can say the area through which the liquid is actually coming out, this is very small, so it means we can say velocity will be more. So definitely velocity will be more, it means we have here square of a velocity, it means this factor is more, clear? And but let's suppose if doctor is utilizing pressure by using thumb, so at the time only the 1 power of pressure is contributing in energy, but here the square of that velocity is contributing in energy. It means definitely we can say if we are using needle at that time, definitely we can say area is very less, that's why we can say flow rate is easily or flow rate is better controlled by this situation, clear? So this is all about this question, clear? Now if I am talking about part number D, clear? In part number D it is given a fluid flowing out of a small hole in a vessel result backward thrust on the vessel, clear? Now let us try to understand. Let's suppose here we have a container, and let's suppose here I am having a very small opening, clear? I am having a container and I am having a small opening, clear? So let's suppose we fill liquid up to this level, clear? And it is given a fluid flowing out of a small hole in a vessel result in a backward thrust. So we can say definitely when liquid is coming out from this hole, definitely we can say area is less, clear? When area is less, it means I can say velocity will be more, Clear? When velocity will be more, it means I can say momentum that will be more. Clear? Because linear momentum is defined as mass into velocity. So actually we know every action has an opposite reaction. Clear? So if we are considering this as an action, definitely a force will also exerted on the wall of this container. Clear? So we can see through this opening, definitely water or any liquid that is going with a higher velocity, momentum will be more, and that's why we can say thrust, that backward thrust that is acting on this vapor, it will also more. Clear? Now we are going to discuss part number E. Clear? So in part number E, it is given a spinning cricket ball in air does not follow a parabolic trajectory. Clear? So dear student, have you seen any fast bowler? So when a fast bowler bowls, actually first it will take some run up. Clear? And after that he throws a ball. Clear? So but let's suppose a fast bowler throw a ball directly. Clear? So definitely we can say it follow a parabolic trajectory. But when that bowler is releasing a ball, actually at the same time he or she is giving some twist to that ball. Clear? And due to that twist, we can see one part of a ball, it is gaining the lower velocity compared to other part. That's why we can say a pressure difference is created, and we can say that ball is actually deviates from its original trajectory. Clear? So we can say that effect is known as Magnus effect. Clear? Definitely you have listened about word outswing and the inswing ball. Clear? So outswing and inswing ball, it is actually occur because at the time of, at a point of release, bowler is giving some twist to that ball, and that's why we can say the Magnus effect is actually occurring, and we can say that actual parabolic path that has to be travelled by the ball, but due to this Magnus effect, that trajectory is not followed. Clear? So this is all about this question. So dear student, we are going to discuss question number 10.5, and in this question it is given to you a 50 kg girl. Clear? So it is given mass of the girl, this is 50 kilogram. 50 kg girl wearing high heel shoe balance on a single heel. Fine. The heel is circular with the diameter 1 centimeter. So diameter of a circular heel, this is given to you 1 centimeter. Now we have to calculate what is pressure exerted by heel on horizontal flow. Clear? So let's suppose we can say, let's suppose this is a girl. Clear? And let's suppose this girl is actually standing on a single heel. Clear? And definitely this girl will exerting a pressure. This girl will exerting a pressure P on this horizontal floor. Clear? Yes. So now we can say how can we calculate here value of pressure. So pressure, this is given by force per unit area. Clear? So value of force we have, we can say because this is 50 kg, so I can say this is 50 g divided by, I can say area we can write like this, this is pi by 4 into d square, I can say this is 10 to the power minus 2 whole square. Clear? So now from here we can say this is 200 g divided by pi into 10 to the power minus 4. Clear? So now we can write like this, pressure P, this is given by 200 into 10 divided by, we can say this is pi is approximately you can say 3.14 into 10 to the power 4. Clear? So I am writing like this, 20 divided by 3.14 into 10 to, this is 100, we can say 10 to the power 6 Newton per meter square. So now we know that this is 20 by 3, so approximately we will find 6.66. Clear? And this is 3.14, so we can say, let's suppose approximately 6.6. So 6.6 into 10 to the power 6 Newton per meter square, or we can say this is equal to 6.6 megapascal. Clear? So this is a total pressure that is exerted by a girl on horizontal ground. Clear? So this is all about this question. Now dear student, we are going to discuss question number 10.6, and in this question it is given to you Torricelli's barometer used mercury. Fine. Pascal duplicated it using a French wine of density 984 kg per meter cube. Fine. Determine the height of wine column for normal atmospheric pressure. Clear? So actually, definitely we know that atmospheric pressure calculation is done by Torricelli sir, and actually from there we are getting height of a mercury column, that is 760 mm of Hg. clear, but Pascal actually uses not mercury. Pascal is using here a French wine having density 984 kilogram per meter cube. So now we have to find what is height of a wine column. So directly we can see pressure exerted by h height of wine column. This should be equal to pressure exerted by 760 mm of mercury column. Clear to you? Yes. So how can we write? We can write pressure. So pressure exerted by, so we can say density of a wine. Clear? We can say rho, G and H of a wine. Clear? This is given by, I can say density of mercury multiplied with G and H of we can say mercury column. Clear to you? So from here we can say density of a wine, this is given 984 multiplying G multiply, this is our objective, height of wine column. Clear? We can say density of a mercury, this is given by 13600 multiply G, and height of mercury column we know, if we are writing here 0.76. Clear? Because this is 760 mm of Hg, I am writing in meter. Clear? So we can say G and G, this is cancelled out. So height of wine column, this is given by 13600 divided by 984 into 0.76. Clear? So now if you calculate, definitely you will find approximately we can say this is 10.5 meter. Clear? So how can you calculate? You can calculate like this. This is 984. Approximately you can take let's suppose 1000. So we can say 1000 divided by something. So we can say this is 13.6. 13.6 is multiply approximately 0.8. So 30.6 into multiplied with 8. So you can say we have 8, we have 4. This is we can say 2. So this one. Clear? So directly we can say, because here we have 2 points. Clear? So 1 point we are taking, so approximately I am getting 10.8 meter. So but correct answer you will find 10.5 meter. Clear? So like this we can calculate height of a wine column. Clear? So this is all about this question. Now dear student, we are going to discuss question number 10.7, and in this question it is given to you, a vertical offshore structure is built to withstand a maximum stress of 10 to the power 9 Pascal. Okay, fine. Is the structure suitable for putting up on top of an oil well in the ocean? Fine. Take the depth of an ocean roughly 3 km. So our objective here in this question is to calculate maximum pressure that is exerted by oil vent, or we can say maximum pressure that is exerted by ocean on that structure. Clear? So how can we calculate? Directly we can say pressure, this is given by rho GH. Clear? Because above this structure we have a sea water, and we are taking here density that is 1000 kilogram per meter cube. I am taking here G, this is also 10. And what about height? Approximately we have to take height 3 km. So I can say this is 3 into 10 to the power 3. Clear? So from here we can say this is 10 to the power 4 multiply 3 into 10 to the power 3. Clear? So from here I can see this is 3 into 10 to the power 7 Newton per meter square. Clear? So we can say this is pressure exerted on that structure by seawater. Clear? And it is given it can stand up to 10 to the power 9 Pascal. So definitely we can say this pressure exerted is less than the maximum pressure that maximum stress that can be generated in that structure. So we can say we are getting this situation. P is less than 10 to the power 9. Clear? It means we can say definitely this structure can withstand for this pressure. Clear? So definitely our objective is what? Yes, definitely I can say, is the structure suitable for putting up? Yes, definitely this structure is suitable. This structure is suitable. And why? Why I am saying like this? Because pressure exerted, this is less than we can say the actually maximum pressure, that maximum stress that can be generated in a structure. Clear? So this is all about this question. Now student, we are going to discuss question number 10.8, and this question is related to application of Pascal's law. Clear? So actually this question related to hydraulic lift. Clear? Now concentrate on the screen. In this question it is given a hydraulic automobile lift is designed to lift car with a maximum mass of 3000 kg. Clear? So let's suppose I am drawing here a simple diagram. Let's suppose this is a given situation. Clear? Let's suppose here we have a piston. Clear? And let's suppose here we have some connecting fluid. This is connecting fluid. Clear? And we can see here we have piston like this. Clear to you? So let's suppose I have here two piston. This is piston number 1. I can say this is piston number 2. Clear? And a hydraulic automobile lift is designed to lift car with a maximum mass of 3000 kg. So let's suppose here we have a platform. Clear? And let's suppose here we have a car. And maximum mass that this piston or this platform can lift, it is all about 3000 kg. 3000 kg. And the cross section area of the piston, this is given to you. Let's suppose this is A1. I can say 425 centimeter square. It means 425 into 10 to the power minus 4 meter square. Fine. What maximum pressure would the smaller piston will have to bear? Clear? So I can say if I calculate here P1, I can say this is given by F1 upon A1. Clear? So value of F1, I can say this is mg. So 3000 multiplied g divided by area. Area is given 425 into 10 to the power minus 4. Clear? So from here you can see we can write like this, 3 into 10 to the power 4 divided by 425 into 10 to the power minus 4. Clear? So now if we calculate here P1, this is equal to 3 divided by 425 multiplied, we can say this is 10 to the power 8. Clear? So this is 425. So how can we calculate here? We can say this is, let's suppose I am taking here, this is 4.25. Listen carefully how I am calculating. This is 30 upon 4.25. So I can say this is 10 to the power 7. Clear? And actually I am dividing here with 100. So I am also multiplied with 100. Clear? So from here I can say this is 30 upon 4.25 and it is multiplied with 10 to the power 5. Clear? Now we know that approximately we can say 4, 7 we have 28. So 7 point something. But here we have 0.25. So approximately I am taking this is equal to 7. Clear? So approximately I am saying approximately 7 into 10 to the power 5 Newton per meter square. Clear? So this is a value of pressure P1. Clear? But what is our objective in this question? Our objective is very clear, is to calculate maximum pressure exerted on a smaller piston. Now you can say from Pascal law we can say that pressure at every point in this liquid will be same. Or we can say whenever we have a static fluid, at that time the pressure is equally transmitted in all the direction. So we can say same pressure is transmitted for this smaller piston. It means we can say P2 equal to P1. Clear? So directly we can say value of P2, this is given by 7 into 10 to the power 5 Newton per meter square. Clear? So we can say we are having same value. Clear? So this is all about this question. Now student, we are going to discuss question number 10.9, and in this question it is given to you a U tube contains water and methane spirit separated by a mercury. Clear? The mercury column in the two arms are in a level with 10 centimeter of water in one arm and 12.5 centimeter of spirit in the other. What is specific gravity of spirit? So again my dear student, this is very simple question. Concentrate on the screen. Let's suppose I am drawing here, let's suppose this is a U tube. Clear? Let's suppose this is U tube. Just a minute. Like this. Let's suppose this is U tube. Clear? And I am saying here, let's suppose up to this we have a mercury. Clear? So let's suppose we have mercury up to this level and mercury is having same level on both the limbs. Clear? Now it is also given here in one side of this liquid we have water. So I am saying, let's suppose I am drawing water like this. Let's suppose here we have water. Clear? And it is given in this question, this water column is having height 10 centimeter. So we can say this one is 10 centimeter. Clear? While it is also given on an other hand. Clear? On an other hand we have a split. So let's suppose this split is actually up to this level and this value is given to you 12.5 centimeter. Clear to everyone? Now what is my objective? My objective here is to calculate specific gravity of split. So if we want to calculate specific gravity, it means first we have to calculate density of this split. Clear? Here we have split, clear, and here we have water. This is water. Clear? And I can say this is mercury. Clear to everyone? So now how can I calculate? So you can say, let's suppose if I am taking here this point number, let's suppose 1, and let's suppose I am taking here point number 2. So we can say at 1 and 2 we can say both pressure are same. Clear? So if pressure is same at 1 and 2, how can I write? I can write like this: P1, this should be equal to P2. Clear? Now I can say pressure at 1, this is equal to density of water G and height of water column. Clear? This should be equal to density of this we can say split. Clear? It is multiplied with G and we can say height of this split column. Clear? So now we can say this G and G, this one is cancelled out. Clear? And now we can say density of water. Density of water we are saying this is 1 gram per centimeter cube. It is multiplied with height of water column. I can say this is 10 centimeter. Clear? Actually we know in CGS unit we have value of density 1 gram per centimeter cube. Clear? And height of water column we have 10 centimeter. Clear to you? Yes. Now if I am talking about density of split, clear, and it is multiplied with height of split. Height of split we can say this is 12.5. Clear? So now we can say density of split. This is given by, this is 10 divided by 12.5. Clear? We can actually write like this. This is 25 multiply 2. Clear? So now we can say this one is 5, we have 2, so this is 4 divided by 5, and we can say this is 0.8 gram per centimeter cube. Clear? So this is what? This is the density of this split. Clear? But what is my objective? My objective here is to calculate value of specific gravity. Clear? So how can we define specific gravity? Listen carefully. How can I define specific gravity? Specific gravity is actually defined by density of a split divided by density of water at 4 degree Celsius. Clear? So yes, now we can say specific gravity as this is density of split divided by, I can say, density of water at 4 degree Celsius. Now we can say here we are getting density in CGS term. So in CGS term we have 0.8 gram per centimeter cube divided by, I can say this is 1 gram per centimeter cube. Clear? So from here we are getting specific gravity, this is 0.8. Clear? So correct answer of this question we have as equal to 0.8. Clear? Now student, we are going to discuss question number 10.10, and actually this question is extension of previous question. Clear? So in this question, in the previous question we already know it is given a U-tube contains water and methyl split separated by mercury. Clear? The mercury column in the two arms are in a level with 10 centimeter and the 10 centimeter of water and 12.5 centimeter of split. Clear? But now let's suppose situation changes. What will happen? If 15 centimeter of water and split each are further poured in a respective arms of a tube, then what is difference in a level of mercury in two arms? Clear? So now let us try to understand this given situation. First again I am drawing here this U-tube. This is U-tube, and let's suppose here this is also again we have a U-tube. Clear? Let's suppose. And let's suppose now we are saying, let's suppose there is some difference in a mercury column now we are getting, and now this mercury will rise in which limb? It will depends on a pressure difference. Let's suppose I am assuming here this is at actual level of mercury now. Clear? Now it is also given, let's suppose I am assuming this is the height of a split column. Clear? So already we know 12.5 centimeter is already filled. Clear? Now we are adding 15 centimeter more. It means I can say this is 27.5 centimeter. Clear? And let's suppose here water is already we have 10 centimeter and we are adding here 15 centimeter more. It means now I can see we have water level up to, let's suppose this one. Clear? And now we have this column, this is 25 centimeter. Clear to you? Yes. So first let us try to let's suppose I am saying here this is a point number 1 and let's suppose this is number 2. So first, can we calculate value of pressure at 1 and 2? Yes, actually it will decide that the mercury will rise in which limb. Clear? So we can say value of P1. P1 is given by rho W G HW. Clear? So density of water, we know in a CGS we are taking this is 1. Clear? Okay. Now if I am talking about G, value of G is what? We can say value of G is what? That is 10 meter per second square. I can say this is 10 into 100. Clear? And I can say this is centimeter per second square. Clear? And what about height of water? Height of water is given 25 centimeter. Clear? So from here you can see pressure we are getting 25 into 10 to the power 3. We can say this is dyne per centimeter square. Yes or no? Because this is pressure, you are getting all values in a CGS. Clear? Density of water we have 1. Clear? G you are taking, that is 10 multiply 100. Clear? And HW you are taking 25 centimeters. Clear? So here you can write unit. This unit you are getting because this is not Newton per meter square, this is dyne per centimeter square. Clear? So I am saying this is dyne per centimeter square. Clear? Now we can also calculate here value of P2. We can see density of this spirit. Clear? Multiply G and H of spirit. Clear? So now we can say density of spirit. Density of spirit is given to you. Yes or no? Density of spirit. YouTube contain this one. Fine. Density of spirit. Actually we calculated in last question, this is 0.8. Clear? So I can say this is 0.8. Clear? I am taking this is 0.8 and multiplied with, I can say 10 into 100. Clear? And multiplied with height of spirit. So height of spirit, this is given by 27.5. Clear? So from here you can say, we can write like this, 27.5. It means 55 by 2. Yes, 55 by 2, and I can say this is 4 by 5 into 10 to the power 3. This is also dyne per centimeter square. Clear? So from here you can say, we can say this is 2 and this one is 11. So we can write like this, 22 into 10 to the power 3. This is dyne per centimeter square. Now from here you can say that pressure at 1 you are getting 25 something and P2, this is you are getting 22 something. It means definitely we can say pressure at 2 is less compared to 1. It means definitely we can say this mercury will rises in a second limb. Clear? So now how can we write? So let's suppose if I draw here this extension, and let's suppose if I am talking about this point, so we can say pressure at 1 and pressure at 3, this will be same. Clear? So what is value of pressure at A? I can say 25 into 10 to the power 3. This should be equal to 22 into 10 to the power 3 plus. Now I will write here density of mercury. Density of mercury, I can say this is G, and height of mercury column. Height of mercury column. Clear? So from here you can write like this. This is 3 into 10 to the power 3 equal to density of mercury. Density of mercury we have 13.6. It is also given specific gravity of mercury. Clear? So if you multiply it with 1, you can say density of mercury is 13.6. Clear? It is multiplied with G. I can say 10 into 10 to the power 10 into 100. Clear? And I can say this is height of mercury column. So I am saying this is H, small h. Clear? So can we calculate? Yes, we can say this one and this one cancel out. So height of mercury column, now this is given by 3 upon 13.6. Clear? So from here you can say 13.3. We have 39. Clear? And 2 we can say that is 26. So approximately we can say this is 0.25. Approximately I am saying 0.25, and we can say this is centimeter. Clear to everyone? So this is all about this question. Clear? Nowadays student, we are going to discuss question number 10.11, And in this question it is given, can Bernoulli equation it can be used to describe the flow of water through a rapid flow in a river. So now listen carefully. Actually Bernoulli equation is actually applicable for a steady flow, or we can say for an ideal flow. Clear? And for an ideal flow there should be some condition. Ideal flow should be steady, incompressible, irrotational. Clear? So now we can say, if we are talking about a rapid flow of a water in a river, at that time we can say when velocity of a water is more, it means it can lead to a turbulent flow. Clear? And Bernoulli equations is only applicable for a streamlined flow. Clear? Or we can say steady flow. Clear? That's why we can say a Bernoulli equation cannot be applied for a rapid flow of a water in a river. Clear? So this is all about this question. Now dear student, we are going to discuss question number 10.12, and in this question it is given to you, does it matter if one uses gauge instead of absolute pressure in applying Bernoulli equation? Clear? So my dear student, do you know what is Bernoulli equation? Bernoulli equation is given by P plus 1 by 2 rho V square. Yes, P plus half of rho V square plus rho GH, this should be equal to constant. Clear? So this is a Bernoulli equation, and we can say actually this is energy per unit volume. Clear to you? Now in this question it is given, does it matter if one use gauge instead of absolute pressure in applying Bernoulli equation? So let's suppose I am saying here, let's suppose here we have a pipe. Clear? And let's suppose we connect a manometer in this position. Clear? Let's suppose here area is changing, and now we also applying one more, actually we are connecting here one more manometer like this. Clear? So let's suppose I am saying here, let's suppose here we have height, this is h1. Clear? And let's suppose we are getting here height, this is h2. Clear? So now we can say, if we are writing here pressure by the difference of these two levels. Clear? So we can say here change in pressure we are getting, this is rho GH. Clear? So my dear student, this rho GH is we have gauge pressure. Clear? This is known as gauge pressure. But the important part is here, we have to clarify that it matters if we use gauge instead of absolute pressure. So my dear, listen carefully. Let's suppose if I am talking about atmospheric pressure, here atmospheric pressure is acting P atm, and here same pressure is acting P atm. Clear? So important part is here, either I am using here gauge pressure or I am using here absolute pressure. Clear? The value does not change. The value will, important concept is here, we can utilize gauge pressure instead of absolute pressure only when there is very negligible change, or we can say there is no change in atmospheric pressure we are finding. Clear? It means we can say whenever the surrounding conditions are not changing, at the time we can say that atmospheric pressure is same. It means we can say simultaneously we can utilize gauge pressure. Clear? Or you can also understand this thing like this. Let's suppose I am writing this equation here, P1 plus 1 by 2 rho V1 square plus, I can say 1 by 2, actually we can say this is equal to rho GH. Clear? This is equal to rho GH. This is rho GH1. Clear? This is equal to P2 plus, I can say 1 by 2 rho 2 V2 square plus rho GH2. Clear to you? So from here you can say, if we write this pressure P1 and P2 in terms of absolute pressure, then we can write like this. This is P atmosphere plus rho GH1. This is for P1, and for P2 you can write like this. This is P atm plus rho GH2. Clear? Yes or no? Clear? So we can say if you are writing here absolute pressure or gauge pressure, it doesn't depend. Clear? We can say this value always remains same. So at the time you can utilize here the gauge pressure instead of absolute pressure. Clear? So this is all about this question. Now dear student, we are going to discuss question number 10.13. In this question it is given to you, glycerin flows steady through a horizontal tube of length 1.5 meter and radius 1 centimeter. Clear? So it is given in a question, length of a tube, this is given 1.5 meter and radius is given to you small r, this is 1 centimeter, or I can say this is equal to 10 to the power minus 2 meter. Clear? Now it is also given in this question, if the amount of glycerin collected per second at one end. So important part is here, it is given mass flow rate. Clear? So I can write like this, this is m dot indicating here mass flowing per unit time. Clear? And this value we have 4 into 10 to the power minus 3, I can say this is kilogram per second. Clear to you? Now what is pressure difference between the two ends of a tube? Clear? It means my objective here is to calculate pressure difference. Clear? So first of all, can we calculate here volume flow rate? Yes. So how can we calculate volume flow rate? It means I can say volume of glycerin flowing per second, this is given by, I can say this is mass flow rate divided by density. Clear? Because we know volume, it can be written like this, mass per unit mass per density. Clear? And I can say this is mass flow rate per density. Clear? So value of m dot, this is given to you 4 into 10 to the power minus 3 divided by, I can say density. So density it is given to you, yes, it is given in a question, yes, 1.3 into 10 to the power 3. So 1.3 into 10 to the power 3. Clear? And here we are getting value in meter cube per second. Clear to everyone? Now we can say what is pressure difference between the two ends of a tube. Clear? So actually we know, if we have a horizontal tube, this is having a capillary tube. So a capillary tube in a horizontal manner. Clear? Why I am saying capillary tube? Because its radius is very small compared to its length. Clear? So I can say, so rate of flow, this is given by pi p r to the power 4 divided by, do you know this formula? Do you know this formula? This is actually 8 neta L. Clear? So rate, volume flow rate, this is given by pi p r to the power 4 divided by 8 neta L. Now what is my objective? My objective here is to calculate pressure difference. So I can write like this, P, this is given by Q multiply 8 neta L divided by pi r to the power 4. Clear? Actually what is Q here? I can say this Q is volume flow rate per second, or you can say directly volume flow rate. Clear? So now I can say this pressure difference, this is given by value of Q. Value of Q is given, that is this one, 4 into 10 to the power minus 3 divided by 1.3 into 10 to the power 3. Clear to everyone? Now it is multiplied with, I can say 8 multiply neta, means we can say viscosity of glycerin, we have 0.83 multiply. If I am talking about L, L is given to you, this is 1.5 meter. Clear? And it is divided by, I can say pi. Pi we can say, I am writing here pi into radius. Radius is given to you 10 to the power minus 2. 10 to the power minus 2 power 4. Clear? Now we have to just simplify and we can calculate here pressure difference. So pressure difference is given by 4 into 8 into 0.13 into 1.5 into 10 to the power minus 3. Clear? Divided by, I can say 1.3 into pi into, this is 10 to the power minus 8, 10 to the power minus 8, and this is 10 to the power minus 5. Clear? This is 10 to the power minus 5. Clear? When it goes to, again I am saying 10 to the power minus 8, this is 10 to the power minus 5, and when it goes to numerator, I can say here we are getting 10 to the power plus 2. Clear to everyone? Clear? Done. So now we have to just simplify and we can get our answer. So dear student, now if we solve it, we can write like this, pressure difference, this is given by 9.8 into 10 to the power 2, I can say this is Pascal, or you can also write in Newton per meter square. Clear? So this is the answer of this question. Clear? So important part we have, that how can you proceed in this question. This formula you should keep in your mind. This is a formula. Clear? And first of all you have to calculate here volume flow rate. After volume flow rate you can easily put all the values in this formula and you can find pressure difference. Clear? So this is all about this question. Now dear student, we are going to discuss question number 10.14, and in this question it is given to you in a test experiment on a model aeroplane in a wind tunnel, the flow speed on the upper and the lower surfaces of the wing are 70 meter per second and 63 meter per second respectively. Okay, fine. What is lift on a wing if its area is 2.5 meters square and density of the air is also given to you? Clear? So let's suppose I am just taking here, let's suppose you can assume this is an aeroplane. Clear? Let's suppose this is an aeroplane. Now in this question it is given upper and lower surface of a wing are having this much of speed. So let's suppose I am saying here we have V1 and this value we have 70 meter per second. Here we can say we have value V2 and this value we have 63 meter per second. Clear? Now it means definitely we can say whenever there is a difference in the velocity we are getting in upper wing and the lower wing, or we can say upper side or lower side of a plane, at that time we can say definitely here we have a pressure difference according to Bernoulli equation. So we can apply here this equation P1 plus 1 by 2 rho V1 square plus rho GH1, this should be equal to, I can say P2 plus 1 by 2 rho V2 square plus rho GH2. Clear to you? Now from here we can say we are assuming, let's suppose this point is 1 and 2. So 1 and 2 is almost at a similar level we are taking. It means we can say this one and this one is cancelled out. Clear? So from here we can calculate pressure difference P1 minus P2. I can say this is 1 by 2 rho V2 square minus V1 square. Now from here you can see we are getting V1 is greater than V2. It means definitely I can say this P1 minus P2 is negative. So P2 minus P1, this one is given by 1 by 2 rho, I can say V1 square minus V2 square. Clear? Now I can put here all the values. So pressure difference, definitely you can say pressure is more on the surface number 2 compared to surface number 1. So definitely we can say whenever we have a pressure difference, due to this pressure difference this aeroplane is taking off. Clear? So now I can write like this, 1 by 2 into density 1.3 multiply, I can say V1 square minus V2 square. So V1 value is given 70. So I can say 70 square minus 63 square. Clear? So from here if you calculate, you can write like this, 1.3 divided by 2 multiply, I can say this is 7 and we are getting this is 133. Clear? So if you multiply, then you can say this is 21, we have 2, so this is 9.1 divided by 2 into 133. Clear? So now just divide it. I can say, let's suppose I am assuming this is 9, so I can say this is 4.5. So or you can say if you multiply 9 with 133. Clear? So from here we can see this is 7, we have 2 left, we have 29, we have 2, so this is 11 by 2. Yes or no? We can say 27, we have 2, so 27 we have 29, then 2 and this is 11. So from here I can say yes, we have one point also, so I can write like this. Clear to you? No, that's fine. 1197 by 2. Clear? So from here we are getting this is 2, we have 9. Clear? We have 8 and then we can say 5. Clear? So 598.5 Newton per meter square, this pressure difference we are getting. Clear? But my objective is what? My objective here is to calculate what is lift. Lift means actually we have to find here what is net force acting on this aeroplane wing. Clear? So I can say if I find here net force, I can write like the pressure difference multiplied with area. Clear? So pressure difference I have 598.5 and multiplied with area. So area is given to you, what is the area? We can say 2.5, so I can say this is 5 by 2. Clear? So if you multiply it with 5 and divide it by 2, definitely you can get here net value of force. Clear? So concentrate on a screen. So I think clear to you. Basic concept is here we will apply first Bernoulli theorem, and after applying Bernoulli theorem, definitely we can say yes, we can find here net force acting. Clear? So net force, if you multiply here, you can write like this, F net, this is given by, if you multiply 598.5 with 5, clear. So we can say this is 25, we have 2, so this is 42, we have 4, we can say 49, we have 4, and this is 29, clear, and it is divided by 2. So if you write here, we can say this is 1, clear, and we can say this one we have 4, we can say we have 9, clear, we have 6, and we can say this one. So 1496.25 Newton net force that is acting on this wing we are getting, clear. So this is all about this question. Now dear student, we are going to discuss next question, question number 10.15. In this question it is given to you figure A and B refer to the steady flow of a non-viscous fluid. Okay, which of the following two figure is incorrect and why? Clear. Now concentrate. Now we can see if you observe both the figures, first of all let's suppose I am saying this one we have 1 and section, this is 2 section, clear, or you can say here we are getting 1 1 dash and this is 2 2 dash, clear. Same we are taking this one is 1 and this one is 2, clear. Now actually you know for a non-viscous liquid, if we apply here continuity equation, we can say A1 V1 this is equal to A2 V2, clear, or you can say right like this, that velocity it is inversely proportional to area, clear to everyone. So velocity is inversely proportional to area. It means if we have area less, definitely we can say velocity will be more, clear. So if you observe here number 1 and number 2, definitely at number 2 you are getting less area, it means velocity will be more, clear. And we can say because both are at the same level, if you are considering here 2 points at the same level, clear, I can say value of h will be same, clear. So if I apply here Bernoulli theorem, I can write like this, P1 plus 1 by 2 rho V1 square, this should be equal to P2 plus 1 by 2 rho V2 square. Now we can say actually this energy per unit volume at every section remain constant, clear. So now you can observe definitely here A2 is less than A1, that's why we can say V2 this is greater than V1, clear. So we can say when V2 is more compared to V1, definitely this P2 will be less, yes or no, because this sum always remains constant, it means pressure at 2 it remain constant, clear. It means when pressure is less, it means we can see if you are talking about this head, so the value of head will be less, yes or no, because we know pressure is given by if you write here this is atmospheric pressure plus this one, this is pressure at 2, yes or no. So now we can say when velocity is more, pressure is less, when pressure is less we can say this pressure head will be small, clear. It means we can say which we have to find which of the two following figure is incorrect. So definitely I can say number 1 is incorrect, clear, number 1 is incorrect. So I can say figure number 2 is correct and figure number A is incorrect, clear. So this is all about this question.